and then we will practice with lab number 5 today. Okay, let's talk about what does it mean by repeatability. Okay, so I will pass the slide about bias. Okay, we have learned about it. So let's move to slide number 36. Okay, and I will show you, okay, what does it mean by repeatability? Okay, so if you take a look at the definition of repeatability, okay, it means the variation, okay, the first bullet, the variation of repeated measurements under similar condition. Similar condition here mean the same part, okay? So if we measure the same parts with the same operator or by the same operator, with the same setup, okay, and same environmental conditions, okay, but we measure it several times, okay, using the same measurer, measure the same part several times, okay. What we expect is that the measurements or the observation or the numbers that we get from the measurement should be exactly the same, right, every time, okay. But in reality, it is possible that several times that we do measurement, it may give different results, different measurements, okay. So that means there is a variation happen, okay, in this case. And this variation is called variation regarding repeatability performance, okay. If, and you know that the statistics that is used to quantify the level of variation is called standard deviation, right? So if we collect the data and then we quantify or calculate the standard deviation from different times of measurement of the same part by the same operator, we will call that sigma, we will call it sigma of repeatability performance, okay? And then we have to appraise whether we're going to accept it or not. Okay, you get that? Okay, and another thing is called reproducibility, okay? So in this case, we look, okay, at the situation where we have several operators or several measurers, okay? So we expect that each measurer should give the same measurements, right? Okay, because if we ask them to measure the same part, okay, so we want them to give the same result. So that means there will be no variation among measurers, or the measurements doesn't depend on the performance of each operator, that we do not want it, because what we really want is to quantify the dimension of the part, right? So if the part is 10.0, okay, we should get 10.0 no matter like which operator we use, right? Okay, so that means we do not want difference or variation among operator. But if it happens, we will call that variation as sigma regarding reproducibility performance. Okay, so if sigma reproducibility is small, that means it's good. Okay, there's less variation, okay, among the operators. Okay, so repeat variation regarding reproducibility. Okay, besides the variation happen from different operators or different measurers, it may come from different setup. Okay, so if we measure the same part, okay, by the same operator, but we set up the measurements, okay, different times, okay, if there is variation, we will call that variation as sigma reproducibility also. Okay, and by different environmental conditions, okay, so that we want to see how sensitive, okay, of the measurements, okay, regarding different things. In this case, different operators, different environmental conditions, different setup, okay, for measuring parts, okay. But mainly we want to appraise the variation regarding the operators. Okay, so up to this point, okay, may I check your understanding just for a few minutes? Okay, so can anybody explain to me what do you understand about the meaning of repeatability, the variation regarding repeatability and variation regarding reproducibility? Okay. Let me see. Okay. But I'll pick up randomized for each one of you. Okay, but or if anybody would like to speak up, okay, please feel free to do that. Okay, let me check now. We have 7 students here. Okay, สวัสดีค่ะนักมล
สวัสดีครับอาจารย์
Okay, okay, who's come more? Parit, right? Parit สวัสดีค่ะ
สวัสดีครับอาจารย์
สวัสดีค่ะ ใครที่อาจารย์ยังไม่ทักไปเนาะสุภวิทย์สุภวิทย์สวัสดีค่ะ
สวัสดีครับอาจารย์
สวัสดีค่ะสุภวิทย์เข้ามาฟังทันไหม about repeatability and reproducibility
เข้ามาฟังทันครับ
Okay, Suphawit, could you please help explain a little bit what do you understand about the meaning of variation regarding repeatability? Or you can pass if you want more time to study.
ขอผ่านนอนดีกว่าครับอาจารย์
Okay, okay. So I'll ask other people, okay, to have explain it to you. How about Nannapat, huh? Nannapat, could you please help what do you understand about repeatability?
So the repeatability is the measure under the same like constraint condition, but
Yes.
On the reproducibility is the measurement under the like different operators.
Okay, so under the same condition, okay, besides, so that's mean for repeatability, so is the variation within one operator, right?
Yes,ค่ะ
And you could explain a little bit more about repeatability. Suppose we pick up, okay, Supavit, okay, please carefully listen to, okay, what we are talking about right now. Okay, so if we have one operator, okay, one operator measure one part, okay, so how variation regarding repeatability happen is when that operator measure that part for one time or several times.
In several times ค่ะ
Yes, okay, several times, okay, and then those several times give different measurements, right? So measurements mean the numbers that we get from when we do, okay, measurements. So measurements in this case mean observations or the numbers that we get, okay? So, but keep in mind that in reality, we will measure a part, okay, just one time, right? Okay, when we want to know the dimension of the part in, in the factory. So generally, we want to measure it several times, right? Usually we measure it just one time, okay? But, and then we will rely on that number. We will believe in that number, right? Okay, that is when we use it, okay? But before we use we do the measurement, we have to appraise first whether we should believe in that number or not. Okay, so that means we have to quantify about the repeatability performance in the sense that if we measure that part, okay, second time or third time, okay, if the second time or the third time, it gives pretty much the same result or very similar numbers to the first time, Okay, so we are more confident, okay, for the numbers that measurement system give us, right? So it doesn't depend on the times that we measure, because in different times, okay, we believe that, okay, or we can rely on that it gives similar results. Okay, so that is the point that we do the appraisal, okay, for precision. Okay, but if when we do appraisal, the second time, okay, is much different from the first time, or the third time is different from the second time and the first time, so we have to worry, okay, that our measurement system is not precise. Okay, that's mean if the first time we get 10.0, so we are not so sure that the next time it may give us the number which is much different, okay, from 10.0, and then we will not be confident about the numbers that we get, that if it's really the true number or not. Okay, so this is the point that we have to do repeatability appraisal, okay, to be more confident. Okay, not just to be more confident, to appraise that should we believe or rely on this the precision of this system or not. So if it is not precise, okay, so we have to fix the measurement system. Okay, and then to do that, we have to find out the cause of variation regarding repeatability, for example. Okay, so we have to check for the gauge. Okay, the gauge means the measurement device. Okay, so if there's something wrong with the gauge, we have to fix it. Okay, so that it will give the precise results. Okay, or it may happen because, okay, if the same operator measure the same part different times, okay, if they do not have well enough work instruction or the steps or the measuring method, okay, so they may use a little bit different methods for different times that they each operator do the measurements, okay, and that it may cause the variation, okay, among different times that operator do the measurements. Okay, so clear work instruction, okay, of how to do measurements, okay, will help reduce the variation regarding repeatability also. Okay, so if there is variation, high variation, we should find out if the measurement method is clear or not. Okay, so if it's not, so we have to make a new work instruction method that is better. Okay, and we have to train the operator regarding the new method. Okay, do you get that? Okay, good, Nanapat. And now let's move to reproducibility. Okay, so variation regarding reproducibility, okay, come from which source, which possible sources? นักพากรช่วยหน่อยค่ะ
ครับ
ค่ะ
ขอคำถามนี้ได้ไหมครับอาจารย์
Okay, so if there is variation happen, okay, regarding what we call reproducibility, okay, performance, so what are the causes of this variation? Or you can tell the meaning of reproducibility. Okay,
reproducibility is the cause of, like, when you produce it again, it has a consistency in the production.
maybe not exactly in this case. Okay, so now, okay, maybe I'll clarify this a little bit. Okay, Now we've talked about the precision of the measurement system. Okay, we are not talking about the precision of the production. Okay, so the precision of the production, like in this case, if we compare. Okay, so remember we have learned about process capability analysis, right? Okay. In that case, okay, we produce many parts, okay, right? Many parts, and then we want to see the difference among different parts. For example, in terms of the length, the diameter of those parts, okay? If there are variation among the parts, we will call that sigma of part, okay? The variation, that means there's the variation or the difference among the dimension of different parts. Okay, but now, okay, in this class, okay, in this content, we have talked about the variation of the measurements. Okay, it's not related, not exactly, it's not the same as the variation of the parts. Okay, so for the measurements, okay, we consider, for example, for each part, okay, so if we take one part, okay, and then if we measure that part several times, and if there are variation or difference among different times, we will call that there is variation regarding repeatability performance. So repeatability, that as we have talked about before, means the variation from the measurements of the same part. Okay, the keyword is the same part, but and also the same operator. Operator here mean the same measurer. Okay, the same one who do measurements. Okay, so repeatability means the variation of different times that they measure, that each measurer measure the same part, okay, within the same measurement, the same measurer, okay. But variation regarding reproducibility, okay, now you have to focus on the same part again, okay. So if you measure the same part, okay, if the factory, okay, for example, has 3 operators that do measurements of this products, okay, and for example, operator A, B, and C, okay, if we ask them to measure the same part, okay, so for the first round, for example, if we ask each one, okay, of the 3 operators to measure part number 1, for example, part number 1, one time, okay, per each operator, okay, so we will get 3 numbers, right, from different operators, okay, and if those 3 numbers are exactly the same, okay, that means there's no variation regarding reproducibility at all, okay, but if those 3 numbers are different, okay, so that means there are the results are different, right, among 3 operators. That means there's variation regarding reproducibility performance. So reproducibility
อาจาร
means
ย์คะแชร์หน้าจอ
อาจารย์โทษทีค่ะอาจารย์ยังไม่ได้โชว์เลยแหละเดี๋ยวโชว์ PowerPoint ไปด้วยได้ค่ะโอเคค่ะงั้นโชว์หน้าจอไปด้วยก็ดีค่ะโอเค like เห็นไหมคะเนี่ยเดี๋ยวนะขออีกทีนึงokay, just a second. Okay, so this line shows you the concept of variation regarding reproducibility. Okay, that means if we have 3 operators, like in this case A, B, C, right? And if we ask each one of them to measure the same part several times, okay, several times. So we look at operator number 1, operator A, okay, so there's the distribution, okay, so the distribution or the variation let me get a pen. So the variation here, okay, within operator A mean sigma regarding repeatability in this case, repeatability, because this variation come from the same operator, right? But different times, okay? So if different times we get different results, so there will be variation, okay? That is called variation regarding repeatability, okay? And then if we ask operator B and C, okay, to do the same thing, that means measure the same part, different times, we will get sigma repeatability, okay, for operator C and operator B also, okay? But, okay, if now we would like to compare, okay, the measurements among different operators, okay, so we will calculate the mean, okay, an average, okay, of the measurements of operator B, A, C, A, B, and C, right? Okay, and then if we take a look at the difference of the average of the maximum of the operator that give maximum measurements, that is operator C, right? This point, okay, at this point, okay, is the maximum average, right? And operator A give minimum average, okay? So that's mean on average, okay, there is this much level of variation or this much difference among different operators, okay, and this, okay, variation is quantified by what we call sigma reproducibility, okay. And we would take a look how do we really calculate this number, okay, from the data sets that we have to collect, okay. But this just want to show you the concept that variation regarding reproducibility means the difference, okay, of the measurements among different operators, okay. We would calculate the maximum difference, okay, among operators, whereas variation regarding repeatability, okay, we consider the variation within the same operators but different times of measurement, okay. Come back again. So maybe I'll go check the understanding a little bit. นันพัฒน์นันพัฒน์หรือเปล่าแม่เมื่อกี้อาจารย์ถามใครไปเนาะณภกรนะปะณภกรใช่ไหม
ครับ
ณภกร okay, now do you understand more about reproducibility?
ครับผม
Okay, could you please give a brief explanation about variation regarding reproducibility? So what does it mean?
It's a variation between across the operators, but not within the operator.
Okay, very good. Okay, and the variation within the same operator, different times. Okay, so what do we call that?
Repeatability.
Yes, very good. Okay. Okay, let me. Okay, see. Now we have 9 students here. Okay, Nanapat, Norapat. Let me check again. Okay. Okay, so now we can move, okay, to the next thing. So if you understand what does it mean by the source of variation, okay, that regard precision. So let's take a look at this model a little bit. Before, okay, I explain this. Okay, so please take a look at the data set first, okay, so that you have ideas about this. Okay, suppose we want to appraise for repeatability and reproducibility performance. Okay, so that means we have to take different operators, okay, and ask them to do measurements, okay? Suppose we have 3 operator, 1, 2, 3, okay? So we can appraise for reproducibility, right? Okay. And if we want to appraise for repeatability, okay, so we will ask each operator to measure the same part. For example, part number 1. We will ask them to measure the same part more than 1 time, right? In this case, 2 times. Okay, it can be 3 times. Okay, I will talk about the sample size or how many times that we should do replication. Okay, later. Okay, like in this case, if they want to appraise for repeatability, so this factory asks each operators to measure the same part 2 times. Okay, as you can see here. Okay, and they have to do the test, okay, for more than 1 part. Okay, so in this case, they ask each operator to measure 20 parts, okay, so that they have like more sample size. And remember that each part actually can have different, a little bit, okay, variation or a little bit different dimensions, okay? So there will be variation among the parts also, okay? From the parts that are small to the parts that are a little bit larger than other parts, okay? Given that it within the same model, okay, same specification. Okay, and let me ask you about this. Okay, so if we take a look at these 2 numbers, okay, operator 1 measure part number 1 2 times. Okay, the first time get 21, the second time get 20. Okay, so do you think that is the variation happen? If that happen, what is the variation is about? Is about repeatability or is about reproducibility or is the variation regarding the part? Okay, anybody can answer me? 21 and 20, okay, are different. So there is a variation that is regarding repeatability, reproducibility, or part. Okay, maybe I'll ask Pawat.
ฮัลโหลครับ
Okay, a little bit louder,
ได้ยิน
please.
ไหมครับอาจารย์
เบานิดนึง โอเค ดังอีกนิดนะคะ
ครับผมได้ยินไหมครับ
โอเคแล้วค่ะ โอเค ตอบได้เลยค่ะ
It should be repeatability ครับ
Yes, very good. Okay, repeatability because these 2 numbers are under the same operator, right? And under the same part. So it's about repeatability. Okay, good. And okay, next, okay, if, okay, I change, okay, this number to 21 and 21. Okay, these 2 number to 21. Okay, this 2 number 20, 20, and these 2 number are 19 and 19. Okay, so if this is the case, okay, so the variation happen, right? Like 20, 21, 21, 20, 20, 19, and 19. So these 6 numbers are different. So that means there is variation happen in the measurement system. And what is the source of this variation? Okay, it's caused by repeatability, or is about reproducibility, or is about the parts. Okay, so Pita, could you please help answer this?
That would be reproducibility ค่ะ
Okay, because
because the measurement varies among the operators.
yes, very good. Okay, good. Okay, and okay, one more thing. Okay, suppose okay, the numbers for part number 1, for example, if it's 21 for, okay, 6 number here, 21, 21, 21. Okay, and part number 2 is 19 for 24. Okay, all 24. Part number 3 is all 20, for example. Okay, and if the numbers are the same for each row, that means the same for each operator with for 2 times. But the difference, there is difference, okay, here, okay, along the column of the part. So what is the cause of, actually we can call the source of this variation? ดีครับภาวัตค่ะ
ครับ
ค่ะ
ครับ
Do you follow my question? Okay.
Can I have the question again?
Question again. Okay. So I suppose that if we get the numbers, okay, that are all 20, 21 in the first part, okay, all 21, 21, like what I wrote here, okay. And the second part, okay, if we get the measurements, that is 24, 24, 24, okay, all 24. And the third part is all 20. Okay, my first question is there is variation? Suppose we consider only 3 parts, okay? If there is variation regarding reproducibility,
No ครับ
okay, because
the number of the measurement is all the same between amongst the operators.
okay, that's very good. And also there's no variation regarding repeatability, right? Because
ครับ
those 2 times are the same, right? Okay, but there's variation, right? In this what we call total variation, there's variation in total because we see different numbers for part number 1, 2, and 3, right? Okay, so the variation that happen in this data set come from which source?
From the part itself.
Yeah, very good, of the part itself. But why the parts have different numbers? ครับพวัน why the parts have different numbers?
It
Why
can
part
be the
number 2
deflection.
has a number about 24, why part number 3 is about 20?
Is that be the can it be the deflection in the manufacturing process?
Yes, very good, because there is a variation within what Pawat said. There's variation within the manufacturing. Okay, that's mean there's variation among the parts. So part number 2, okay, when we produce it, okay, if we do turning process, okay, suppose this is the diameter of the parts, okay, so part number 2 has a little bit larger diameter compared to part number 3, which is smaller, okay. There is variation in the production, okay, that is caused the variation of the parts, right? Okay, and the point of this thing is that actually we have to accept that when we do production, there is variation among the parts, okay, so it's normal that we will have variation among the parts, okay, and then we want to measure the this variation among the parts, right? For example, if part number 2 is large, like about 24, okay, we really want to measure that. We want to we want to have the measurement, which is about 24, okay? And when we move to measure part number 3, which is about 20, okay, we really want the number to be around 20, okay, so that we would get the true results from the measurements, right? Okay, but the things that we do not want is that suppose part number 3 is about 20, okay, so if the first time we get 20, okay, we measure and then we obtain 20, that's good, right? But if the second time we get 21, okay? So that means the second time is not good, okay? Because it's different from the numbers that it should be, right? And, okay, if we measure, okay, only one time, and if we get 21, okay, so that means we will believe that part number 3 is 21, right? If we have this operator 1 to measure it, we will believe that this part is 21, but actually it's 20, okay? So that means we get incorrect result, right? So that means, okay, if our measurement system is good, okay, so we want the difference among different times to be small, okay, so that, okay, the measurement is not depends on different times of measurement, or it doesn't depend on different operators, okay, and if it doesn't depend on operator or doesn't depend on the times that we do the measurements, okay, so we hope that the result that we obtain, okay, is a good result, okay, and that result, if there's no bias or is accurate also, that would be the best, okay, that means we can believe in terms of the accuracy and in terms of the precision, okay, so the measurement doesn't depend on the operators or doesn't depend on the times that we do the measurement. That is the best thing, okay? And then we can believe in the performance of the measurement system, okay, to distinguish among the parts, okay? So distinguish among the part means if the part is large, okay, we will have large measurement. If the part is small, we get small measurements, okay, and it's precise, okay, because it's not depending on an error, okay, or different among operators, okay, that is what we want, okay. So when we do measurement system analysis, okay, we have to set our mind like this. First, we have to okay, accept that there is a variation among the parts, okay? And variation among the part, actually, we quantify it using process capability analysis, right? Remember that CP number is used to quantify whether the sigma among the parts is too large or not, okay? So if we want to measure the variation among the parts to see if the variation of the parts is acceptable or not, when we will do what we call process capability analysis, okay? But when we do MSA, we have to think about it as different thing. So we have to think about that, okay? Given, okay, a CP or sigma part, okay, level, okay, it can be large or small, okay, we do not care at this point, okay, but if, for example, if the variation among the parts is large, we want our measurement system to tell that the variation is large, okay, to be correct as, okay, is actually B, okay? But if the variation is small, okay, we want our measurement system to tell that it's small, okay? So the reality can be sigma of the part can be large or small, okay, or medium, okay, whatsoever, but we want the measurement system to tell us the truth, okay? That is what we have to set our mind, okay? And to tell that whether the variation of the measurement system is good or small or not. Okay, come back to see this model, okay? So why IJK mean the observation or the measurements from I mean operator I, okay? I'm sorry, I mean the part, okay, part effect, mean part I, okay? For example, Y1, 2, 2, okay, mean the measurement from the measurement of part number 1, okay, by operator J, okay, operator number 2, okay? And 2 here, the index K here mean the round that they do the measurement, okay? So for the second round that they do the measurement, okay, of part number 1, okay? And this number depends on, okay, mean here mean the overall mean of all parts and all operators, okay? It's called the grand mean, okay? And the observation is also depend on the amount of bias, okay, of the measurement system, okay? And it also depends on the part effect, okay? If the part is large, okay, for example, part number 2 is large, so it tends to give the observation to be large, right? Okay, so it depends on the part also. And it also depends on the operator, okay? So if operator number 2 tend to give large measurements, okay? So if that part is measured by operator number 2, okay, we tend to have large observation. And it's also depending on the interaction effect. PO means interaction effect among the parts and the operator. Okay, I will talk about that, okay, later. And also, okay, the last component is what we call random error. Okay, so it means, for example, if we measure it by measure the first part by second operator the first time and compare with the second time, okay? If there is variation, okay, in statistics we say that, okay, we do not know the source of this variation because the variation actually this variation came from the same part, right? The same part and also the same operator, but different times of the measurements, okay? So the error that happened or the difference that happened come from random source, okay? We cannot tell that is come from operator or parts, okay? So we will call that this is called random error, okay? And if we take the variance, okay, if we calculate the variance, okay, of each component, okay, so variance, we will get variance of observation, okay, or which we call variance total, okay? So variance total means if we take a look at the data set again, okay, in this data set we have 20 parts, right? We have number of all observations, okay, will be 20 parts times 3 operators, okay, and each operator measure 2 times. So we have 120 observations, okay, in this data set, right? From observation 1 here, which is 21, to the last measurement, which is 17, okay? So this 120 observations, okay, the numbers are different, right? And then if we take this observation and then we calculate what we call, let me show you, okay, what we call sigma total, okay? So like in this case, n here is 120, okay? If we use the simple standard deviation formula, okay, to calculate the variation among 120 or all observations, okay, we can use this formula, right, to calculate. And then we get sigma total of, for example, 3.34, okay? So this variation, okay, come from different source, okay, because it is the it contains the observation in the whole table, right? And this variation, okay, come from the variation among the parts and also variation among operators, right? And also variation regarding different times, okay, that they do measurement for each operator, right? So sigma total is a function of three things here, okay? And what we have to do is that given this much variation of the data that we have, okay, we want to quantify how much, okay, variation is caused by the gauge, okay? Gauge here mean the measurement system, okay? Measurement system, okay, let's come back to the model. Okay. So, okay, if we take the variance, okay, of the observation, we will get what we call variance total here, okay? And mu is an average of all parts, okay? It is a constant. So if we take the variance of the constant, it will be 0, okay? And also the bias is also a number which is constant. So the variance of the bias will be 0 also, okay? So the next part is the variation, okay, of the parts, okay? Since different parts have different dimensions, right? So there will be variation among the parts, right? You will see that the variation of mu and p, so mu and bias b, okay, is not in the model because it's 0, right? Okay, so there is the variation start with the variation among the parts, and also the variation total, okay, is have some part which is about the variation among different operators. Okay, so O here mean operator, and also variation regarding what we call interaction effect. Okay, I will explain this to you by the graph, okay, in a few minutes. Okay, but at this point, okay, I want to show you that, okay, there's variation among the parts, among operator interaction, and also variation regarding repeatability, okay, or random error. Okay, so there are 4 main parts, okay, of the variance total that we observed in the data sets. Okay, and then if I rewrite it, okay, in this slide, okay, we will see that the variance total that we observe in the data set, okay, come from 2 main sources. The first one is the variation of the part or product, okay, is the same thing, okay, and the second part is come from the measurement system, okay, and the variation among the measurement system, we can call it variance of the gauge also, okay, and then it separates into 2 main parts. So the first part is regarding repeatability, and the second part is regarding reproducibility, okay, and reproducibility actually can be divided into 2 sections. What we call variance regarding the main effect of the operators, and the variance due to the interaction of the operators and the part. Okay, so reproducibility mean is the sum of 2 things, which regarding the operators, okay, the interaction and the main effect. Okay, and come back to this point. Okay, so what we want is that we will use the measurement system, right, to quantify the variation among the parts, right? We want to use the measurement device to measure the dimension of each part, right? Okay, so if the part is small, we want to tell that it's small. If the part is large, we want to tell that it's large. Okay, so we want to quantify, actually we want to quantify the variance of the parts, right? Okay, but we need to use the measurement device, okay, to get the number. So that means the variation that we really observed total here is what we really observe, or the numbers that we that we get, okay, is also include the variation of the measurement, right? And if the variation of the measurement is 0, if you take a look at this, if I assume that if this is 0, so that means what the variation that we observed is exactly equal to the variation of the real parts, right? So that is perfect. That is the best thing that we can do, we can get, okay? We observe exactly the same as the variation of the parts that really happen, okay? But in reality, the variance of the measurement is not 0, right? Because there may be difference regarding repeatability and also variation among operators, right? So what we have to do is that, so we have to calculate the ratio, okay, of this thing, the variance of the measurement, and then we have to compare it with the variation total, okay? So if the ratio of the measurement system compared to sigma total is small, okay, is small. In the criteria that we use to accept this is less than, okay, 30%, okay, less than 30%, okay. So if this ratio is less than 0.3, that means the variation among measurements, okay, that come from the measurement system is small enough, okay, to be able, for us to be able to use that measurement system to measure the variation of the parts, okay. You get the concept, okay? So the concept is that given, given any variation of the part, because sigma total contains sigma part also, right? Given any level of variation among the parts, okay? If we can prove that the measurement, the variation regarding the measurement is small, okay, compared to the variation of the parts, we will believe that the measurement system is precise enough to be able to use it, okay, to distinguish among the parts, to distinguish the variation of the parts. Okay, so that is the key concept of this thing, okay. Okay, and now we will move to the indicators or performance indicator that we used, okay, to compare, okay, the variation of the measurement system to see if it's large or not, okay. So the first indicator is what we call precision to tolerance ratio, okay, which is, okay, precision here is quantified by the variation of the whole measurement system, okay, and is quantified by 6 sigma of measurements, okay. And if 6 sigma is large, that means precision is poor, right? And then tolerance is, okay, you know that it's a difference between upper spec and lower specification limits, okay? And sometimes we use 5.15 instead of 6, okay? If you have, okay, basic knowledge about statistics, okay, you know that 6 sigma, okay, range cover 99.73%, okay, of the variation of the measurements, okay. So if we use 6, that means we use 99.73%, okay, to quantify the variation of the measurements, okay. But if we use 5.15, okay, that means we use 99.0. Okay, so it depends on you. You can pick up any one of them. Okay, but in Minitab, okay, Minitab use 6 as default. Okay, so after the break, okay, we will practice on the workshop. Okay, and then we will use Minitab to calculate these indicators for you. Okay, given the numbers or the data set that you plug in. Okay, it will automatically give you this ratio. So you have to know that in Minitab, it used 6 sigma instead of 5.15. Okay, this is the first indicator. So we compare the variation, right, of the measurements with the tolerance. Okay, so if the tolerance is large, okay, means we allow for large variation of the part. So this ratio has to be, okay, less than 0.3. Okay, that means we have to keep this ratio to keep the variation of the measurements to be less than 30% of the tolerance. Okay, that would be good. Okay. The second indicator is what we call precision to total variation. Okay, so the same thing, precision is quantified by 6 sigma, so SD is sigma, right, of the measurement, or we can call this sigma gauge. Okay, same thing, or we can call it sigma total GR&R. Okay, we can call it for different names. And for this indicator, we will compare it with total variation. Okay, not tolerance anymore. Okay, so total variation here is 6 sigma total. Remember 6 sigma total. Sigma total is quantified by all data points. Okay, all data points that, okay, include sigma of the parts and sigma repeat and sigma reproduce, right? Okay, so it's like we compare. One more thing that I have to tell you is that for sigma part, we cannot directly quantify it because when we want to tell the difference among the parts, right, we have to measure it with the measurement device. Okay, that means there will be variation of the measurement to be confounded, okay, or combined with the variation of the among the parts. Okay, before we, so for us to observe the variation among the parts, we cannot avoid, okay, the variation of the measurements because we need to use the measurement device to measure the parts, right? We cannot know the variation of the part without measurements. Okay, so that's mean when we talked about the variation total, okay, so that's mean we consider the variation of the parts, okay, but we have to accept that there will be variation of the measurement system, okay, add on it, okay, but if this portion is small, okay, that's mean when we compare, okay, the variation of the measurement, we can call this like, variation of the measurement, right? So if this portion is small compared to the variation of what we want to measure, that is sigma total, so that would be great. Okay. So we have two indicator, P to T and P to TV, right? And then we will use this criteria for acceptance. Okay, so if we have this ratio to be, okay, greater than or equal to 30, that means the variation is of the gauge is too much. So we will not accept this precision. Okay, so, and if it's less than 10%, that is acceptable for sure. Okay, the range between 10 and 30, it depends on each company. Okay, so if we strict with the precision, we will use this ratio at 10%. Okay, but if we are flexible, okay, for the precision, okay, we can use 30% to accept it. Okay, so if it's for example, 20%. If we use this criteria, we will say that this precision is not acceptable, right? But if we compare with 30%, okay, so we can say that the precision of 20% is acceptable in this case. Okay, so first we have to design which criteria you will use, okay, 10 or 30, okay, or 20, it depends on you, okay, but generally we do not use the criteria of over 30, okay, that's too much. For like 40% is too much, okay. And then most important thing is this thing, okay, since we have two indicators, okay, so when we design whether to accept the precision or not, okay, actually we should focus on this indicator only, okay. We will not base our decision, okay, on P to T ratio, okay. We will make decision based only, okay, on this indicator. That means we will compare the precision level with the total variation. Okay, that is more important than compare it with the tolerance. Okay, and the reason is that, okay, we want to use the measurement system, okay, right, to measure or to quantify the variation of the parts that we produce, right? So that's why we need to compare it with the total variation. For example, if the total variation of the part is this much, okay, so we want to keep the precision to be like less than 30% of this, of the whole range here, okay. And if our parts, okay, has this much variation, okay, we have good CP, okay, value. For example, our variation of the part is small, so it's really important, okay. So if we want to distinguish the part among this range, okay, so it's necessary for us to have the variation of the gauge to be smaller than the first situation. That means this amount should be less than 30% of sigma total. Okay, do you get that? So the precision or the variation of the gauge, okay, that we allow or we accept really depends on the variation of what we are measuring. If we are measuring the things that has large variation, we can allow for large variation of the gauge. But if the things that we are measuring has small variation, so we have to have better precision, okay, to be able to distinguish the part within that small range. So that's why we have to keep the ratio of the precision to the total variation to be at some number, some specific number, which is 30%. Okay. But tolerance, okay, tolerance actually is the allowable variation of the parts that we produce, right? Okay, so it's not the main things that we need to compare, okay? So because the main purpose of the measurement is to quantify the variation of the real process, okay? The real process can be large or small, okay? So we have to compare with that, okay? But to compare with the tolerance, okay, just tell us, okay, just for informing us, okay, how much variation of the gauge comparing to the tolerance, but we do not use it, okay, as the indicator to make decision, okay. So we can calculate it, but we will not consider it, okay, when we make decision. I hope you get that concept. Okay, do you have any question about the indicators? Okay, let me review a little bit, right? Okay, maybe I'll randomize one of you to help explain what you understand. Okay, but if you do not understand clearly, so I will try to make all of you to understand it clearly before we move to the workshop. Okay, so have I talked to Narapat yet?
ครับ
Narapat คะเราคุยกันยังเช้านี้
น่าจะยังครับ
ใช่ยังใช่ไหม Narapat could you please explain what you understand about why do we have to use or to compare okay what let me revise. Could you please explain why do we have to consider the indicator P to TV, okay, to judge whether we're going to accept the variation of the measurement system or not? You can explain what does it mean by P to TV ratio, how it's calculated and what does it show? You can refer to this slide. Okay, let me write it down one more. Okay. Okay, in short, P means quantified by 6 sigma of the gauge, and TV is 6 sigma total. Okay. Okay, based on this formula, Narapat, could you please explain why do we have to consider this ratio to make decision?
To check for the tolerance and error.
Not tolerance in this case. Okay, now we are talking about the total variation, okay, of the process. Okay, tolerance is another indicator, 6 sigma, okay, of the measurement system with the tolerance. Okay, so now I'm talking about this, okay, indicator.
To check for the variation of the gauge compared to the overall performance.
Yes, overall variation of the parts that we produce in our production process. Okay, right. That is the lower part here. Okay, and okay, what does it imply? Okay, if this ratio is high, what does it mean?
It means that the variation is not high.
Okay, if this ratio, okay, is small, right? It's small, that means the variation of the measurement system is not high, right?
ครับ
Is that what you want to say? Okay. And okay, what is the maximum ratio that we accept?
10%.
Okay, good. We can use 10% or 20% or 30%. Okay, it depends on you. Okay. So if we use 10%, okay, that's mean, so how do we make decision based on this criteria that you said?
If the ratio is less than 10%, it means that this variation is acceptable.
Yes, okay, very good. Okay, that means we accept the precision of that measurement system. Okay. And okay, one more thing I'd like you to know, okay? So we accept P to TV of, for example, less than 10%, okay? So P means 6 sigma of the gauge, right? The measurement system, and TV means 6 sigma of the total here mean the process, which mean, okay, the composed of the variation of the parts also, right? Okay, so suppose, okay, remember when we do process capability analysis, okay, so if this CP number is large, okay, it's large, like it's over 1.3, oh, no, sorry, it's less than 1.33, right? Remember that? If it's less than 1.33, okay, that means sigma of the process, okay, is too large, right? So what do you need to do next? Okay, maybe I'll ask Supicha. Supicha, if we do process capability, right, and then we found that sigma of the process of the sigma of the part is too large, what will you do? Supicha คะอยู่ไหม
ค่ะ
Remember when we do process capability analysis, right? We have two approaches, like to move mean to the target or to reduce the variation, right, of the parts. So if the variation of the parts, or what we call variation of the process, is too large, which can be seen by the CP number, right? If it's too large, what will you do?
I can't remember.
Okay, actually it's pretty simple. When variation is large, right, we should try to reduce the variation. Is that right? Reduce it by, for example, make a clear work instruction method, okay, of how to produce the part, so that every part will be produced by the same method. That can help reduce the variation, right, of the process, right? Okay. And okay, so Picha, again, if we reduce the variation of the process, if you take a look at this formula, okay, when the sigma of the process is reduced, what will be the effect on P to TV? This ratio P to TV, what will be the effect? It will be higher or will be lower if the sigma process is smaller?
Higher.
Yes, higher. And is that a good thing when P to TV is higher?
No.
Yes. No, it's not good, right? Okay, let me give you some number. For example, if before we reduce the variation of the process, suppose this ratio is equal to, for example, 8%. 8%. Okay, so Bichaka, is it acceptable if this ratio is 8% compared to the criteria of 10%?
Acceptable.
Yes, okay. So first is acceptable. Okay, remember this first, acceptable. But now, okay, when we do PCA, right? And then we find that CP is too large, or it's too small, sorry, too small. Okay, so we will improve the process by reduce the variation of the process, right? And then Supicha has okay, told us that it will give the P to TV ratio to change, right, to a higher level, right, to a higher percentage. Suppose now it becomes, for example, 15%. 15%. So if this number change your decision regarding the performance of the precision of the measurement system. So in short, now if P to TV has changed to 15%, will you still accept the precision of this measurement system? ถามนักกมลบ้าง
What's the question นะครับอาจารย์
The question is that when we reduce, okay, the variation of the process, and then we get higher P to TV ratio, and if we get 15%, but now if P to TV is 15%, okay, we use the criteria of 10%, okay? So what will be your decision regarding the precision of the measurement system? Will you accept it or do not accept it?
do not accept it ครับ
right do not accept precision right so I want you to notify this that first we accept right the precision but now we do not accept it okay why what is the factors that contribute to whether we accept or do not accept it in this case ค่ะนักกมล
sigma gauge เหรอครับ
No, not sigma gauge. Okay, we do not suppose we do not improve anything about the gauge, but in this case we reduce the variation of the process. Okay, the process here mean variation among the parts. Okay, remember PCA, right? Process capability analysis. Okay, we quantify the variation or the difference among the parts that we produce. Okay, different parts that we produce, right? And if the parts are too much different, okay, so we want the part to be similar to each other, right? And the way to make the part to be similar is that we should have a standard method for production. For example, the same method for each operator to make parts, okay? The same setting of the machine over different parts, okay? The same working methods, okay? With that standard, okay, we can reduce the variation of the parts, right? And the key point of this thing is that when the variation of the part is too large, okay, so usually engineers would like to reduce the variation of the parts or what we call the variation of the process, okay? And when the variation of the process is changed to a smaller number, that will make the P to TV to be increased, right? And in this case, if it increased to a number that is not acceptable, right? So what you need to do next? So now if the P to TV is higher than the criteria, right? So now your decision is that you will not accept the precision at the current level of precision anymore, right? So what you need to do next? Nakamonkan, do you follow me?
I think I don't know ครับอาจารย์
Okay. So that's okay. Okay. Now, okay, maybe you will listen to another friend. Okay, maybe we will learn from each other also. Parit, can you answer me? Okay, if now you reduce the variation of the parts and then you get unacceptable precision of the measurement system, what will you do next? What should you do next?
ไม่รู้เหมือนกันครับอาจารย์อยากฟังเพื่อนมากกว่าครับ
โอเคใครรู้บ้างคิดดีๆมัน very simple ถ้าเกิดเรา open mind นะ very simple now we do not right accept the precision of the measurement system because the key point is that if the variation of the process is this much we have to keep this ratio to be 10%. But now the process variation reduced to this much, right? Okay, maybe I'll compare to this. The variation of the process reduced to this much. Okay, so the variation of the measurement system, now if it stay at the same level, okay, before is 8%, but now if the variation of the parts is the same, okay, but the base, okay, that it has to compare with is reduced, so it will make this ratio to be greater, okay, but what we really want to do is that given any variation of the process, we have to keep this ratio to be 10%, okay, so if the variation is this much, we can allow for this much variation of the gauge, But if the process variation is smaller, we have to reduce the variation of the measurement system to keep this ratio to be 10% all the time. Do you get that? I'm not sure. I hope you get that. So in this case, we are at this point, okay? So before is 8%, but now, okay, we have reduced the variation, okay, of the process, but we do not do anything about, we do not improve or reduce the variation of the measurement system. So it stayed the same, okay? That's why it make this ratio to be higher, okay? And it's greater than 10%, right? So we do not accept it, right? But before this is less than 10%, we accept it. Okay, so now we are up to this situation that we get this ratio to be higher than acceptable criteria, right? So what do you need to do next? Given this much variation of the process, what do you need to do next? So Pawit, do you have any idea? So Pawit อยู่ไหมคะ
ไม่รู้เหมือนกันครับอาจารย์
โอเคไหนลองอิสรีอีกคนนึง If we cannot, okay, accept the precision of the measurement system, that means the variation of the measurement system now is too much, right? It's too much to use to measure the variation of this process, which is now small. Okay, so if the variation of the measurement system is too much, so what do you have to do?
Reduce the range, the same range หรือเปล่าคะ
The same range? What does it mean?
Reduce the variation ของที่ตอนแรกบอกว่า accept อะค่ะใช่ไหมคะ
Okay, very close. Okay, so we have to reduce the variation of the gauge, okay, or the measurement system, right? To keep this ratio, for example, this is 15%. Okay, so given this much variation, which is reduced sigma of the process, right? Process. Okay, so we have to reduce the variation of the measurement system, okay, to keep this ratio to be less than 10%. Do you get that? Because now our decision is that the precision is not good, right? The variation of the measurement system is too large. So the answer will be very simple. So what we have to do next is to reduce the variation of the measurement system, okay, to keep this ratio to be less than 10% again, right? And to reduce the variation of the measurement system, you can either reduce the variation regarding repeatability or reduce the variation regarding operators, right? Okay, so you can like train operators to be more consistent. Okay, so you can check the gauge, okay, so that it will give higher repeatability performance. Okay, this kind of thing to improve the precision of this measurement system. Okay, to have it ready, okay, or good enough to measure the variation of the process that is now small. Okay, so before what we are going to measure is large, okay, sigma of the parts that we want to measure is large, So we can allow for large variation, okay, of the gauge. Okay, but now, okay, since the variation of the process is small, okay, so this large variation is not acceptable anymore, right? So we have to improve it or to reduce the variation of the gauge, okay, to have good enough precision to measure this small variation of the parts. Okay, that is the key point. Okay, so to summarize, okay, the variation of the gauge that we allow, okay, should be considered relative to the variation of what we are going to measure. Okay, so if the things that we want to measure has small variation, we have to keep the variation of the gauge to be small and keep that ratio to be less than 10% or 30%. Okay, it's up to you. Okay, so pick up the criteria first and then maintain that ratio. Do you get that? Come back to นัทกมล or Parit or Supavit นะซึ่ง okay you are not understand, you do not understand before, but now I want to make sure that you understand it, okay, right now. So 3 คนนี้ใครก็ได้ช่วยอธิบายนิดนึงได้ไหมคอนเซปต์ตรงนี้ที่อาจารย์ต้องการสื่อให้พวกเราเนี่ยเราตอนนี้เข้าใจว่ายังไงเอ่ยไหนลองใครสักคนได้ไหมคะอาจารย์เรียกนะ นัทกมลช่วยอธิบายเท่าที่เราเข้าใจอยู่ตอนนี้หน่อย
So we need to change the criteria to according to the precision or sigma, right?
No, we do not have to change the criteria. The criteria should be fixed. What do you mean by criteria? Criteria, for example, 10% or 30%, right?
Yes.
Okay, so we have to pick. We have to select the criteria first, whether you're gonna use 10% or 30%, for example. So if you decide to use 10%, okay. So what should you consider next?
The gap sigma gap.
Okay, so you need to quantify this number, right?
Yes.
Suppose you use the criteria of 10%, okay? And then you have to quantify P to TV ratio, right? Okay, so if it's 8%, okay, what's next? What is your decision?
It is acceptable.
Okay, and remember, okay, the case I told you that, okay, you accept it, okay, but the next thing is that an engineer reduce the total variation, okay, or the process variation, and then when the upper part is reduced, it will make this ratio to be greater. Is that right?
Yes.
Okay, but now suppose it comes up to 15%. 15%. Okay, so what is your decision now?
Do not accept ครับ
Okay, and repeat it one more time. And when you do not accept it, what you need to do next?
I don't understand ครับอาจารย์เมื่อกี้
เหรอโอเคงั้นเดี๋ยวลองใหม่ได้ไหมพาริเข้าใจขึ้นหรือยัง
เข้าใจขึ้นนิดหน่อยอะครับอาจารย์
เข้าใจขึ้นนิดหน่อยช่วยเติมหน่อยได้ไหมที่เราเข้าใจมากขึ้นจากสเต็ปตรงนี้ไปเข้าใจไหมเอ่ยว่าต้องทำอะไรต่อ
improve อะค่ะเพื่อคือตอนนี้ ค่า v มันน้อยใช่ไหมครับอาจารย์
ค่าอะไรมันน้อยนะ
ค่า v อะครับ
TV total variation ใช่ไหมนี่เราหมายถึงนี้ปะ
ใช่ใช่ครับผม
ใช่อันนี้มันน้อยลงค่ะน้อยลงเพราะเราทำให้พาร์ทที่เรา produce มาหลายๆพาร์ทมันใกล้เคียงกันมากขึ้นซึ่งมันเป็นสิ่งที่ดีใช่ป่ะที่เราควรต้องทำโอเคเนาะสมมติเราทำเราพาร์ทมันมี variation น้อยลงแล้วพอมันมี variation น้อยลงแต่เราไม่ได้ไปปรับปรุงระบบการวัดคือเราไม่ได้ไปลด variation ของระบบการวัดเราเพราะฉะนั้นตัวเศษเนี่ยคงเดิมใช่ป่ะตัวเศษเนี่ยคงเดิมแต่ตัวหารมันน้อยลงใช่ป่ะ
ครับ
มันก็เลยทำให้ ratio นี้มากขึ้นแต่คีย์เวิร์ดของเราคือเราต้อง keep ratio นี้ให้ less than 10% all the time ใช่ไหม
ครับผม
So okay, so now เราก็เลย do not accept this much variation of the gauge, right? Okay, so next what เราเลยต้องทำอะไรเพิ่มตอนเนี้ยพอเราไม่ยอมรับมันแล้วเราบอกว่า variation ของ gauge มันมากไปแล้วเราต้องทำอะไรต่อล่ะ
แก้ไขปรับปรุงอะครับ
ปรับปรุงที่ไหนนะคะ
ที่
ปรับปรุงเรื่องอะไรเอาแค่ปรับปรุงตัววัดอะไร
ตัวเกรดอะครับ
ดีมากก็ต้องลดความผันแปรที่เกิดขึ้นจากเกจใช่ไหมดีมากเพื่อพอเราลดตรงนี้ลงก็แปลว่าตัว p เราลดลงใช่ไหมคะทีวีเราตอนนี้เท่าเดิมแล้วก็คืออยู่ที่ระดับที่มันน้อยลงตรงนี้ใช่ป่ะเราก็เท่าเดิมอยู่พอเนี้ยตรงนี้ลดลงนี้ลดลงมันก็มีสิทธิ์ที่จะเป็นไงต้องลดลงจนถึงไหน
ซิกมาครับ
ใช่ต้องลดซิกมาของเกจลงใช่ป่ะจนกระทั่งเรโชนี้เป็นไง
น้อยกว่า 10% ครับ
จนก็ต้องลดลงตรงให้มันน้อยกว่า 10% ให้ได้อีกรอบนึงถูกไหมคะมันถึงจะ accept ใช่ป่ะ variation ของระบบการวัดอันใหม่อันนี้ถูกไหมนะคะงั้นคีย์เวิร์ดตอนนี้อาจารย์ก็ต้องการที่จะบอกว่า variation ของระบบการวัดมันจะยอมให้มากให้น้อยแค่ไหนมันขึ้นอยู่กับ variation ของสิ่งที่เราจะวัดเห็นไหมงั้นถ้า variation ของสิ่งที่เราจะวัดมันน้อยระบบการวัดของเราก็ต้องมีความเที่ยงมากๆคือ precision ดีมากๆที่จะวัดไอสิ่งที่มันแตกต่างกันน้อยๆได้เจอโอเคไหมคอนเซ็ปต์ก็คือแบบนั้นนะคะซึ่งมันก็ quantify ออกมาเป็นตัวเลขที่ว่าต้อง keep this ratio to be 10% โอเคนะกำมวลพอเข้าใจมากขึ้นไหม
เข้าใจแล้วครับ
โอเคดีจ้าโอเค now okay a little bit before maybe now it's 10:40 okay so let's have a break okay and after the break I will talk about the lecture just a little bit okay and then we will start to do workshop about okay in 11:10 okay so now let's have 15 minutes break okay and then we'll come back Okay, let's come back. Okay, now let's see the data collection method a little bit. Okay, so in this data set, we have seen that when we have 3 operators, in this data set, they collect 20 parts, right? And use and measure 2 times for each part. And actually, when we do data collection, we have to consider this sample size table. Okay, it will tell you how many parts that we need to do experiments, and also how many replications that we need to do for each part. Okay, and these numbers depend on the number of operators that we have. For example, suppose we have 3 operators. 3 operators, okay, and we are appraising, for example, 1, okay, or 2 measurement device. In this case, suppose we have 1 device, okay, so we have to collect 10 parts and then do 2 replications, okay. So if this is your information, Supavit, could you please help, okay, discuss about this a little bit, okay. In this case, in this data set, we have 20 parts with 2 replications. Okay, so could you please comment on this, that if this sample size is enough, or is it too much, or anything that you can tell about the sample size and the numbers that we really need from this table. So Pavika, are you there?
ครับอาจารย์
So, okay, so in this data set, okay, suppose we have 3 operators to be appraised. Okay, so actually, how many parts should we collect based on this table? Suppose we are appraising 1 measurement system.
3 part ครับ
No. First, we have to take a look at the number of operators, right, that we have. In this case, we have 3 operators, is that right?
yes
Okay, and then suppose now we have 1 measurement device. Suppose we are appraising a vernier, okay? So we have those 3 operators to use that vernier, okay, to measure the parts. Okay, so how many parts that we need to test in this table? How many parts do we need? Take a look at this จำนวนชิ้นงานใช่ไหม so how many parts do we need to collect จำนวนชิ้นงานน้อยที่สุดที่เราต้องการ
คือ
10 okay and ดูมาถึงตรงนี้แล้วค่ะ how many times that we need to do replications for each part how many
ก็2 นาทีครับ
yeah 2 right okay
2
2 okay so now let's come back to the data that somebody else okay have given you. So could you please critique on this? Okay, so the number of replication, is it okay? 2 times each, is it okay?
ครับ
Okay, and how about the number of parts that we have done the test? Is it enough?
It is enough ครับ enough
It's enough, okay, because we need 10, right? We need 10,
yes
but now we have 20. So could you please do we really need 20?
not really ครับ
Yes, actually we really need 10, right? So
ครับ
so
need 10
okay, so if we can redo this, so we can do only 10 parts, okay? It will save your time, right? So you don't have to do number 11 to 20 because it will take unnecessary time for doing this experiment. Is that right?
yeah ครับ
Okay, ka. Good. Okay, so before you get the information, so please take a look at the necessary number of data points that you really need, okay, from this table. Okay, next, okay, after we have obtained the data, okay, so if now I will lead you to how do we do analysis, okay? And I will show you the basic formula to calculate each element of the variation, okay? And then we will move to Minitab, okay, to help you to do the calculation. Okay, so if we want to quantify the sigma repeatability number, okay, so the formula is R bar over D2, okay? So R bar actually is simply an average of R bar for each operator. So what does it mean here is that, take a look at the data sets. Okay, so take a look at, okay. Take a look at the first part for operator 1, okay? So the 2 times different by 1 unit, right? And for the second part, 1 unit. For the part number 4, no difference, right, between 2 replications, so R is 0, okay? So if you take an average of the R, okay, for all the parts for operator 1, you will get R bar 1 equal to 1. So, okay, so what does it mean here? It's Sarika. Could you please help explain what does R bar 1 represents?
Represent the average value of the difference between two measurements ใช่ไหมคะ
ใช่ค่ะ very good, exactly. Okay, so what does it tells you? It tells you about the performance regarding repeatability or reproducibility.
Repeatability ค่ะ
Yes, good. Okay, so it tells you the repeatability of operator 1, right? Okay, so and then you can do the same thing, okay, for operator number 2, right? And then you will get R bar 2 and R bar 3, right? Okay, and then if you take an average of R bar 1, 2, and 3 again, okay, so what does this number tells you? This number is called R bar because we average all R bars again, right? So what R bar represents? Okay, and this formula, okay. We average because okay, Isari told us that each R bar tells you the difference, right, or the variation regarding repeatability for each one for each operator, right? Okay, but if we average those numbers again, so what does it mean by R bar? Isari, could you please help answer one more question?
Is it the average value of the R bar?
Right. Exactly. Yeah. But what is the more insight meaning of this? Okay, so let me suggest. Okay, so an average of R bar, okay, so it means that, okay, we do not consider each operators, but we consider overall system, okay, overall operators, that on average, if we pick up any one operators, okay, and then ask he or she to measure 2 times, okay, the two measurements will be different about this much. Okay, so it's the average, okay, among all operators, okay, for 2 times of the measurements, the difference of the two measurements. Okay, it doesn't depend on the operator anymore because it's just an average of all operators. Is that okay? So it will give you the variation regarding repeatability, okay, of this measurement system, right? Okay, and then to convert, okay, this variation R bar to a number which is called sigma, okay? So in statistics, okay, method, okay, we have to divide it by a constant called D2, okay? This is the constant that we can look up from the table of control chart constants, okay? So remember that when we do control charts, we have to open the constant A2, D4, D3, okay? In that table, we have a constant called D2 also. And if you look up that table, okay, at n, okay, and a constant D depends on sample size n. And in this case, is the number of observation per part per operator. So it means in this case, it means the number of replications, like in this case, per part, for each operator, we measure 2 times. Okay, so 2 is sample size or n that we need to use to look up for D2 number. Okay, so if I plug in the number, okay, I will get, okay, D2 when n equal to 2 is 1.128, okay, and then we will get the number for sigma repeatability, okay. This is an easy formula to calculate sigma repeatability, okay. And next we will calculate sigma reproduce, okay. Sigma reproducibility, okay, is R of x bar divided by a constant D2, okay, again. But now R of x bar, okay, you know that reproducibility tells you performance regarding different operators, right? So an easiest way to quantify this is that you have to calculate what we call x bar of each operator, like operator 1, okay? Operator 1 measures 20 parts 2 times each, right? So operator 1 gives 40 measurements, okay, in this, okay, area that I, okay, mark here, okay? So if you take an average of this 40 data points, you will get 22.3, okay? And you will do the same thing for operator 2 and 3. So you take an average of the same 20 parts 2 times, right? For operator 2, it will give you 22.28 and 22.1 for operator 3, okay? And next, if you want to quantify the variation among operators or the difference of the measurements among operators, okay, so it makes sense that you look for the maximum value, okay? So an operator that gives the maximum value is operator 1, right? 22.3, okay? 22.28 is in the middle. The minimum one is at operator 3, okay? So this 3 operator give difference by how much, okay? That is what we want to quantify, okay? And the easy number is that we will take the difference between the maximum value 22.3 and the minimum value 22.1, okay? And the difference is 0.2, is that right? 0.2, okay? So the difference is called range, right? It's called range, but it's the range of x bar, right? So in the formula, it's called this number as R of x bar, which is okay, which is R of x bar, which is the difference here, which is 0.2, okay? And then we need to convert this number to a statistical sigma, okay, by divided with a constant D2. And again, you have to look up D2 from a table with the sample size. And in this case, sample size to look up D2 number is the number of operators that you are considering. Okay, in this case, you have 3 operators. So the sample size is 3. That is used to look up for D2 table. And now you obtain 1.693, okay? And then you plug into the formula. Now you can calculate sigma reproducibility, okay? So that makes sense, okay? It's very easy formula to quantify how much difference of the measurements among 3 operators. Okay, and now you have obtained sigma repeat and sigma reproduce, right? And then you can plug into this formula, okay, sum the variance of these 2 variance, 2 sources of variance, and then you will get the total variance of the gauge or the measurement system. Remember that you cannot sum sigma directly. If you want to sum sigma, so you have to convert it to variance first and then sum variance. And then if you want to obtain sigma, you will have to take square roots of the total variance, okay? But total variance, you have to sum the variance of each, okay, of all elements, okay? So you need to do this to quantify sigma gauge, okay? And then you will use this number to find out P to TV ratio, right? Okay, remember P to TV, P is 6 sigma gauge. Now you have obtained it, okay, 1.03, okay? And now you have the lower part, which is 6 sigma total. And sigma total, okay, I've mentioned it before that you can use this formula to calculate it by plugging in, okay, the number n, okay, in this case is the total number of data points that we have, which is 120, okay, 120 observations here, okay, come from 20 parts times 3 operators and times 2 measurements each, okay? So if you have to do it by calculator, okay, you need to plug in 120 numbers in there, okay, to quantify sigma total, okay? And now we are ready to calculate P to TV ratio, okay, which is this formula, okay, 6 and 6 will be crossed out, and then we will have this ratio as sigma gauge, okay, 1.03 divided by sigma total, okay, and then this is 0.31 or 31%, okay, and if you use the criteria of 30% anyway, okay, it's not acceptable, right? So we can conclude that we do not accept the precision of this measurement system because if we use the criteria of 30%, the P to TV of 31% is greater than the acceptable criteria, okay? And if you want to calculate the precision to tolerance ratio, you can do it, plug in USL and LSL, right? Okay, and then this percentage just give you the variation of the measurement system compared to the tolerance, okay? And we will not use it, okay, to make decision. We'll make decision based on P to TV ratio, okay? So this is the formula to give you an idea of how do we quantify, okay, each element, okay, of the variation, okay, sigma repeat, sigma reproduce, sigma gauge, sigma total, and convert those numbers to P to TV ratio, okay, and make decision, okay. But okay, now okay, a little bit more, okay. So since this ratio is too much, right? So we will not accept it, okay. And if that is the case, we have to tell like which components we should improve. So you have to come back, okay, and you will see that sigma repeatability is now 1.02, right? Whereas sigma reproduce is much less than sigma repeat, right? So if we have to improve sigma of the gauge, we should focus to improve sigma regarding repeatability. Okay, and we have to find out the cause. Okay, the reason why we do measurement by the same operator on the same part, but different times, why it different too much. Okay, so you have to check for like the understanding of that person or of each person, right? About the criteria, about the method for measurements, or you can check the precision of the gauge. Okay, those kind of thing that you have to find out the reason for sigma repeatability, and then you can fix that cause, right? And then sigma repeatability will be reduced, and you will get P to TV ratio to be at some number which is acceptable. That is the approach for making improvements. Okay. And now, okay, I want to show you, okay, if we want to do gauge and RNA study using Minitab, okay, Minitab will give you the result like this, 6 pictures here, okay, and the numbers from ANOVA study, okay, and there's a lot of numbers here, and one of them is P to TV ratio and another one is P to T ratio, okay, and then you can use this number to make decision. Like in this case, P to TV is 28%, so if you use 30%, you will accept it, okay. And okay, I will explain this, okay, using the workshop. Okay, so now we are done for the lecture part. Okay, now let's start to do the workshop. Okay, so let's open up the file, the Excel file. Okay, from course view, right? Okay, lab number 5. And okay, in this case, if you take a look at the data that we have, okay, they are pressed. Okay, I will ask each one of you very quickly. Okay, so be prepare. Okay, you to be ready to respond. Okay, simultaneously. Okay, in this case, we have measurement device, which is vernier. Okay, vernier caliper, and then we have 2 types of vernier. The first one is called manual vernier. Okay, manual vernier. Do you have you ever used vernier? Okay, so you have to read, okay, the measurements or the observation by your own, okay, on the scale of the vernier. And the resolution is 0.05, okay. That's mean for each, okay, the scale, okay, is different by 0.05 millimeters, okay. And we also have another vernier, which is called digital vernier. Okay, for digital one, okay, it will give you the number, okay, on the screen so that you don't have to read it, okay, on the scale by yourself. Okay, you just look at the number on the screen. Okay, and the resolution is better, which is a higher, okay, resolution of 0.01. Okay, so look at the number. If the resolution is 0.01, that means, for example, operator 1, part 1. The first time, 24.91, right? And the second time is a little bit different, okay? Different by 0.01, okay? 0.01 millimeters, okay? But, okay, for the manual vernier, okay, the resolution is worse, okay. Let's take a look at number, let's see. Okay, this part, okay, operator number 2, okay, number 2, the first time he tells that it's 25.05, right? And the second time is 25.10, okay? So the minimum difference is 0.05, okay, according to the resolution here, okay? And if the resolution is 0.05, he cannot tell like 25.05 and 25.06 because it cannot tell the resolution or the difference by 0.01 because the minimum difference is for each, okay, measurements is 0.05. Okay, you get that? Okay, this is the resolution. Okay, and you will see that it will end with 0 or 5, 0 or 5, okay, because resolution is 0.05. But for the digital vernier, okay, the last digit can be any number 1, 2, 3, okay, 1 to 9 and 0 because resolution is 0.01. Okay. In this case, they have 4 operators. Okay, 4 operators. Okay, so if we take a look at the sample size first, okay, so look at this table. Okay, we have 4 operators, right? Okay, so Nanapat, could you please tell, okay, from this sample size table, if we have 4 operators, how many parts do we need and how many replications do we need? If we have 2 measurements device here, right? Manual one and digital one.
Okay, so we need 2 part, measurement part, and for at least 10 replication.
You switch that. You switch it. We need 10 parts with 2 replications. Is that right?
Okay, ค่ะอาจารย์
Okay, because we have 4 operators, right? So we have 3 or more, which is 4 operators, and the number of devices that we have now is 2, right? Manual and digital. Okay, so we are at this line, right? Okay, so we need 10 parts and 2 replications. Okay, come back. Right, so they took 10 part, okay, and 2 replication, so it's okay, right? And then okay, this team calculates the x bar and average. Take a look at this. If we take a look, calculate the average, okay, of the 2 measurements for part number 1, we will get x bar, okay, and if we take the difference of the 2 measurements, we will get R column, okay, and then we can calculate x bar, which is an average, okay, of all parts here, and average of R, okay, for operator 1. Okay, and then we can repeat that for operator 2 to 4, right? Same thing for digital vernier, right? Okay, so this is the data set, okay, that we have, okay? And then if we need to do the analysis with Minitab, okay, you have to arrange this data format into the format that Minitab requires. And the format that Minitab requires is like this, okay? It needs 3 columns, actually 2 columns for each device, okay? For example, manual vernier, okay? So you have to mention that this observation comes from which operator, okay? So if you have operator 1, we need another column, which is the part column, right? For example, we have 10 parts, okay? Operator 1 measure 10 parts, okay, the first round, okay, and obtain this 10 observations, okay, right? So you just copy it from the data, the table that you have seen before, right, onto this, okay? And now he might have done it for you, okay? And if you see next that operator 1, okay, measure each part for the second round, right? So for the second time, we will plug it in here, okay? So you don't have to tell Minitab that this is the first time or the second time, okay? Because Minitab will know, for example, if there's operator 1 here, part 1 here, and now you have operator 1, part 1 again. So Minitab knows that this is the second round, okay? And then you enter the number for operator 2, 2, and 3 also, right? And then you will get, okay, 80 data points. Okay, and then you have this column for manual vernier and another column for digital vernier. Okay, and then, okay, now Pima will show you that if you plug in this data set, okay, into Minitab and then have Minitab calculate the output of the analysis for you, okay, how can we do that? ค่ะพี่มายช่วยโชว์น้องหน่อยนะคะ
ค่ะ ค่ะ ก็ copy ข้อมูลมาใส่ mini tab นะคะ แล้วก็ไปที่ stat ไปที่ quality tool ค่ะ ไปที่ gate study แล้วก็ไปที่ gate study cost ค่ะ
โอเค แล้วพี่ใหม่ค้างไว้ตรงนี้ก่อนนะคะ Okay, it's in quality tool section under gauge or gauge study. And then if you take a look under gauge study menu, okay, we have seen before like gauge bias and linearity, right? Study, we have done that. And now we are doing what we call gauge study. And then it has crossed, it has nested method. Okay, so in this case, you have to know that if our experiment is non-destructive, okay, that means if we measure this part, so for example, if operator 1 measure the first part, okay, for the first time, okay, if he or she can repeat the measurement for the second time, this is called non-destructive test, okay? But if you have, and then you will click on cross, okay, gauge IR cross for non-destructive test, okay? But if you are you have the case that is destructive test, that means, for example, operator 1 measure the strength of the part, okay, and then he has to, okay, press the part, okay, until it breaks before he obtain the strength value, okay. So if he want to measure that part again for the second time, he cannot use that same part anymore, right? Because it's broke, okay, already. It has broken already. So he has to take the new part, okay, to measure for the second time, okay. So this is called destructive test, okay. But when they pick up another part to measure for the second time, okay, they have to be very careful that he selects the part which is very similar, okay, in the values of the strength compared to the first part that he do it for the first time. Okay, so it's like they have to prepare the data set like what we have for non-destructive tests, but for the same part, okay, let me show you this data set again. Okay, for destructive part, okay, for part number 1, for example, this two, maybe I'll get let me get a pointer for a second. Okay, so for part number 1, okay, if it's a non-destructive, okay, sorry, I have to share the screen, right? Okay. Okay, let me get a pointer. Okay, so if it's a non-destructive part, Okay, so part number one can be measured by all operators, right? 2 times each. That means part number one will be measured for 6 times, right? Okay. And then you will use gauge cross, okay, method to calculate the numbers, related numbers, okay? But in the case that you have destructive tests, okay, so these two numbers will be on different parts and also these numbers, right? Okay, but the structure of the analysis is that these 6 parts that are actually different 6 parts, right? It should be very similar, okay? Should be similar, and we can assume that those 6 parts are identical, and then we count it as the same part, which is part number 1, okay? So you have to be careful when you pick up the parts, okay? And those 6 parts should come from, for example, the same lot, very close in the production time, using the same operator when we do production, same setup of the machine, so that we are pretty sure that those 6 parts are very identical, okay? And then you can move to part number 2, okay, which may come from different times, okay? Different lot of materials, for example, okay? So it can be different among the parts, but within the same part number, it should, all those 6 parts should be the same as much as possible, okay? And if you can collect the data like that, okay, you can plug in this data set into Minitab, okay? And then if it's a destructive test, okay, you will use the mshare เลยค่ะ you will use the method which is called gauge IR nested, okay? So the formula to calculate sigma for each component will be a little bit different from in case of non-destructive tests, okay? So, okay, in this case, you will use crossed, okay? And if you click on that, it will ask you to enter the column of part number, okay? So you double click on part, okay? And operators, you have, okay, operator columns and measurement data. Okay, now let's do manual vernier first, okay? You double click on that, and then you click on, พี่หมายจะไม่ค่อยเห็นเลย
option ค่ะ
options, okay, options, and then you will see that there's number 6, okay, in the first box, right? So it will tell you that for P to TV ratio, it will use 6 sigma instead of 5.15, okay? And then it will ask you to enter the specification limits so that it will use this number to calculate P to T. Remember that precision to tolerance ratio, okay? So you will enter the spec, which is เท่าไหร่นะคะพี่มายบอกน้องหน่อย
tolerance บวกลบ 0.25 ค่ะ lower spec ก็จะเป็น 24.75 upper spec เป็น 25.25 ค่ะ
ค่ะ okay, so if anyone has Minitab, you can, okay, follow this, okay, so that you know how to enter the data, okay? แล้วก็มีอะไรอีกนะคะ ไม่มีแล้วเนาะ
ไม่มีแล้วค่ะ กดโอเคเลยค่ะ
okay, อันอื่นก็ไม่มีอะไรแล้วค่ะ and then click on okay, and then it will give you the picture, okay, and the numbers in the station outputs, okay? And nowพี่มายเดี๋ยวนะคะพี่มายช่วย copy output อะค่ะไปที่ Word ให้หน่อยนะเดี๋ยวจะได้ขยายดูใหญ่ๆนะคะ And now let's take a look at the picture first. The picture is in the Excel file. Maybe I'll share my screen, okay? And the picture is now on Minitab worksheet, okay? For manual vernier, you will get this, okay, outputs, right? And then from this outputs, okay, there are 6, okay, boxes here, okay? So the one, okay, maybe I'll get a pen first, okay? Okay, this is the R chart, okay? This is the X bar chart, okay? And if you take a look, there's, okay, 1 to 10 here is part number 1 to 10 for operator number 1 here, okay? So each point means the range of the two measurements for each part, right? For part number 1, operator 1, and the second one is the range for the part number 2 from operator 1, okay? And then you have this for operator 2, operator 3, and operator 4, okay? And if you take a look at the average, so X, for example, this point is the average of 2 times that operator 1, right? Measure part number, suppose this number 6, okay? So this is the information that Minitabs give you, okay? And okay, next you have to be able to interpret, okay, the numbers here. So, okay, the first thing that you need to do is to know is that each R number represent sigma in terms of repeatability, right? Because it's different among 2 times of the measurements, okay? And X bar shows you the dimension, right? How large or small of the dimension that you measure, okay? So equal, actually, usually equal to 0 mean is good, right? There's no variation among the 2 measurements, is that right? Okay, and then you see that a lot of points are 0, and for some points are 0, sorry, 0.05, 0.01, okay? And okay, I like to tell you this, okay? So R equal to 0 means that it's good, but in some case it may, okay, but in some case it may shows that the resolution of the measurement device is not enough or is too rough, okay? For example, if 2 parts, okay, if 2 parts has this much dimension, 10.11 and 10.13, okay? So if the resolution, okay, is up to 2 digits, okay, up to 2 digits, you will see that the difference is 0.02, is that right? Okay, but if the resolution is rough, okay, it can shows you only 1 digit, okay? So now resolution is 0.01, right? But if it can shows you only 1 digit, which is the resolution is only 0.1, okay? So the first time, okay, you will measure as 10.1, and the second time, okay, 10.13, it will show only 10.1, is that right? So if you calculate the difference, it will be 0, okay, it will be 0, okay? But now it's 0, it's not because 2 parts are not different, but it's because that this resolution is too rough, so it doesn't see, okay, the difference in the second decimal place, okay? So you have to be very careful about this thing, okay? And to judge whether the resolution is enough or not. Like in this case, the manual vernier has resolution of 0.05, okay? So to judge whether the resolution is enough, you have to count the number of different R's value from the R chart. Like in this example, okay, the number of R charts, okay, in this data set is number 1. R is equal to 0. If you see, this is the first number 0, the second number sorry, it's 0.05, maybe 0.1 here, okay? And let me see, 0.1. This is the first number, the second number, the third number, the fourth number, okay? And now it's the fifth number here, okay? So there are 5 different numbers of R, okay? And then to judge whether the solution is enough, we need at least 4 different numbers, okay? So in this case, it has 5, okay, so it's enough, okay? And if you take a look at the numbers for digital vernier, okay, same graph, you will see that there are many more different numbers of R. Okay, if you take a look at this, okay, graph, sorry, take a look at this graph, okay, you will see like this one number, second number, third number, right? Fourth number, fifth, okay, 5, like 6, 7, 8, 9, 10, 11 different numbers, okay? So much more than 3 or more than 4 that we require. So the resolution of digital vernier is enough because actually resolution for digital is 0.01, right? Which is higher resolution and give you many more different numbers of R. Okay, that is the first thing that you need to appraise about whether the resolution is enough or not. In this case, they are enough for both manual and digital vernier. Okay, and the next thing that you need to be able to detect is that from this graph, okay, you will see, okay, there's 2 numbers, right, which is very high. Okay, most of the numbers are between this range, right? Okay, but this 2 number is very high. So if that is the case, okay, that's mean for example, for operator 2, when he measure part number 5, 2 times very much different by 1 unit. Okay, I have to take a look at the data set. The first time is 24.8 and the second time is 25.8. Okay, so if that, and also the same thing here, okay, and if that is the case, okay, so you have to think about this. Okay, what can you think about this situation? Do you think is abnormal, or if those 2 data points is believable? So you have to wonder about this. Let me check. So you think it's possible that these 2 numbers are different by this much, whereas other data points are different by not that much? Okay, and the reason for this is that when they figure out about this, they knows that, okay, in the second time, okay, when do the measurement, okay, they record this number wrong. Okay, so actually it should be 24.8, okay, 24.8, but he wrote it down wrongly. Okay, he wrote it down like 25 instead of 24. Okay, so that caused this number to be an outlier. Okay, the number that is very abnormal. Okay, so when they find out that this This is the reason for this. So, and it's also the same for these 2 points. So they delete these 2 data points out of the data set. This is called data cleaning, right? So we have to clean the data to obtain only the data that is believable or that is true numbers, okay? So that's why we have another data worksheet, which is called data after delete, okay? After we have deleted those 2 data points, okay, we will have another scale, okay? Now the maximum will be I'm not sure, okay. Okay, for 0.10, okay, point 10, 0.15, actually for 0.15 here, okay, instead of 1 in the previous data sets, okay? So next you have to use this data set, okay, to do further analysis, okay, whereas in the digital vernier, okay, results, okay, it doesn't give you abnormal data points, so you can use the original data points for digital vernier, okay. And next, okay, next the graph that let's see, okay, may I move this a little bit over? And just a second. Okay. Okay. Now let's take a look at the outputs again. Okay. So if I look at the digital vernier, okay. The upper part tells you, okay, the percentage. Please take a look at only the blue color, which is called percent contribution of the variance. Okay, so in this picture, it tells you that for 100%, okay, you see here, 100% of the variance, okay, is explained, okay, by the parts, okay, for about this much, 99 point something, but you cannot read it from this scale, right? It doesn't tell you that much details, okay? And if you just take a look at if you want to take a look at this number, you will say that from 100% of total variation is explained by the part variation about this much. It's explained by the gauge, okay, about this much, okay? And the variation of the total gauge is divided into 2 sections, which is repeatability by this much and reproducibility by this much, okay? And if you want to take a look at the real number, okay, so you have to take a look at the session output, which is, let me move it, which is, there's the picture here, okay. If you take a look at the outputs, from the session, it will tell you this table about percent contribution for total variation. It counts as 100%. This is the variance, okay, numbers, and that it converts total variance into 100%, okay, and then it quantifies the variance of total gauge R&R, okay. Actually, first is quantify variance of repeat, variance of reproducibility, okay, using the formula that we have seen before, okay, but Minitab have adjusted the formula, okay, to have more statistical property, okay, but the similar is pretty much, okay, have the same concept as what we have seen before, okay? And we obtain this numbers of variance, okay? So if you sum up these two variance, you will get this number, okay? So this two number come to this number, okay? And reproducibility actually is variation regarding operators, right? Okay, so this two number is the same for this case, okay? And then when you quantify the total variation, which is this number, if you take this number and then subtract by this number, you will get sigma variance of the part, okay? So this number cannot come by itself, so you have to subtract this number, okay, with this number, okay, to get this number. And then for each number, you compare it with the total variance, and then you will get this column, percent contribution, okay. And then you will see that 97% come from the part and 2% come from the measurement system, okay. And the variance total of the gauge, okay, are mainly from repeatability, okay, and it's very small for reproducibility, okay. And this number corresponds to what you have seen in this, okay. So this number will be 97 something percent, okay, and this number is 2.14, right, percent, okay, here. Okay, so this number is here, 98, 97, okay, 0.86 is here. Okay, you follow that? Okay, come back. From the graph again, okay, if you take a look at the graph on the right hand side, okay, this graph compare the measurements for 10 parts, okay, and then for each dot it represents, okay, 6 actually the measurement from all operators, okay, and it connects the line for the average, okay, of each part, okay. So you will see that part number 4 and number 6 have higher dimension, okay, in this case higher diameter, whereas part number 5 is pretty small, okay. And the next graph is comparing operators, okay. So the connected line here shows you an average, okay, of the measurement from each operator, okay, and then you will see that the average is pretty much at the same level, okay. And this variation shows you the variation among the parts, okay. So 10 parts with 2 replications, right? So this is the variation among 20 measurements from 10 parts to rep for each operator. And the last picture tells you the interaction plot between parts and operator. So you will see the label here. There are 4 lines, okay? The blue line for operator 1 and the purple line for operator 4, okay? And then you will see that for part number 1, right? 1 to 6, if you see, okay? There's 6 parts, okay? So different operators tend to give the same measurements, okay? You will see that those 4 lines are, okay, at the same position, right? But look at part number 9. Number 9, okay? Operator 2, okay, tend to give larger measurement, whereas operator number 1, right, the blue one, tend to give lower value, okay? So that's mean, okay? If we take a look at part number 9, and the observation that we get, okay, depends on the operators that do the measurement, right? Okay, if it is measured by operator 2, you tend to have this much value, right? But if it's measured by operator 1, you tend to give lower values, okay? It's not the same for part number 1, okay? For number 1, for operator tends to give very small difference, okay? So that's mean the measurements for which part, okay, is dependent on the operators, okay? In general, okay, so part number 7, 8, 9, 10, okay, tend to have interaction effect between part and operators, okay? That means the measurement depending on both part and operator at the same time, okay? So this interaction part tells you like this in this sense, okay? But the next step is that you have to test whether the interaction effect is statistically significant or not, okay? And also the difference among four operator is statistical difference or not. So we have to take a look at the what we call the result from ANOVA table. Remember ANOVA table in statistics course? Okay, let me check. Okay, this is first. Okay, it will give you the ANOVA table with interaction. So in interaction, first you have like look at the source first, okay? So we have total, okay, variation, and then it will divide it into parts and also gauge, okay? So gauge has 3 main source: the main effect of operator, the interaction amount part and operator, and also repeatability, okay? And then if you want to judge whether the interaction effect, okay, like in this line, is significant or not, so you will take a look at the p-value. Remember, if the p-value is larger than alpha of 0.05, you will say that it's not significant, okay? So in this case, it's greater than 0.05, so interaction not sig, okay? So if interaction is not significant, so you have to take a look at when you move to judge whether the part are different or not, or four operators are different or not, you will take a look at the table without interaction. Okay, one more time. When interaction effect is not significant, you will take a look next at the table without interaction to judge whether the part, the operator different or not. In this case, operator are not giving significant difference because p-value is greater than alpha, right? So there is not significant difference among operators, okay? And for the part, p-value is less than 1.005, which is less than alpha of 0.05 again. So you will say that there is significant difference among the parts that we produce in terms of the dimension, okay? But those four operators do not give significant difference. Okay, do you follow that? Okay. And okay, maybe we cannot, okay, finish this workshop in class, but I will give you as the homework, okay, to fill out, okay, the answer, okay, to these questions, okay? So for example, first question is interaction effect significance. Okay, I have told you before, okay, for now I showed you about the digital vernier, right? Okay, in this case, you will say that is not significant. Okay, for example, you will say that it's not significant. You can write it down, okay, neatly by yourself. Okay, it's not significant because the p-value interaction effect is 0.155, right? Which is which is greater than alpha, okay, of 0.05. Okay, that is what I expect from you, okay? So you will repeat this analysis with the manual vernier, okay? But remember that you have to use the data in the worksheet after delete. Remember that, okay? Because in the manual vernier, we have 2 points that are outliers, right? 2 points that are outliers, so we need to delete these 2 points, and then you have to use the output from this worksheet, okay, for manual vernier, and then for the digital vernier, the output is in Minitab worksheets, okay, and then, okay, you can redo this by yourself for manual vernier, okay, and then next, do operators are giving different measurements? Okay, we have seen before that when interaction is not significant, so you will take a look at the table without interaction, right? Without interaction, and then repeat the same thing. You mention about the p-value of the operators, okay, to answer this question. Okay, next question. Do you think the precision of this measurement system is acceptable? Okay, to answer this question, so you have to come back to look at the next output. Okay, below the ANOVA table, let's see, digital vernier, right? Okay, for okay, you have seen the percent contribution, okay, and process tolerance, okay, you have enter is 0.5, okay. So from this information, this is the variance, okay, column. Okay, if you take the square root of the variance, okay, square root of this column, you will get the column which is called standard deviation, right? Standard deviation, okay. And the source are the same, okay. Total gauge R&R, and then it divide into repeat and reproduce, okay. And reproducibility, it has operator main effect. In this case, interaction effect is not significant, so it removed from the model. But in the case that interaction effect is significant, so you will have another line, which is the part times operator, which means the interaction terms, okay? And then you will get another p-value for that. Okay, come back. Okay, now it calculates sigma for each component for you, okay? And then this column just multiply sigma, okay, from this column by 6. That's all, okay? And then you can calculate P to TV ratio now, okay? So P to TV, remember that is sigma of the gauge, right? Divided by 6 sigma total, okay? So 6 sigma total is this number, okay? Sigma total, okay? And then here you get this, and 6 sigma gauge is this number, okay? This is column of 6 sigma, and total gauge R&R is in this line. So this is 6 sigma gauge, and this is 6 sigma total, okay? So if you take this number divided by this number, you will get 14.6%. And this number is P to TV ratio. Okay, so Minitab will not tell you that this is P to TV ratio, but you have to be able to know it by yourself, that the column percent study variation, and the first line is the P to TV ratio. Okay, and same thing, this is P to T ratio, precision to tolerance ratio. because it's compared with the torrents. Okay, so in this case, okay, let me ask, sorry. Okay, one person here. Okay, we'll take a few minutes and then we'll end the class. กริดเพิ่งมากริดคะ
ครับ
กริดช่วยตอบอาจารย์หน่อย From these numbers, okay, will you accept the precision of the digital vernier? Which number should you take a look at? กริดได้ไหมกริดเข้ามาตอนไหนนี่ได้ฟังทันถึงตอนไหนไม่รู้นะ ได้ไหมคะกริดตอบได้ไหมข้อนี้ จะผ่านไหมหรือตอบได้จ๊ะ
เดี๋ยวลองผ่านก่อนได้
โอเคงั้นไปทวนนะเดี๋ยวไปทวนนะไปตามกับเพื่อนนะ งั้นขอนันภัทรแล้วกันนันภัทรช่วยตอบอาจารย์หน่อย accept ไหมคะ
So for the repeatability, it's unacceptable.
Okay. When accept, okay, so first you don't have to pay attention to repeat or reproduce. You have to pay attention to the whole or total gauge INR performance first, okay? And the numbers that you should take a look at is which number?
Percent variance.
Percent variance. Which number? Tell me the number.
14.62.
Good. This is called P to TV ratio. Okay. Percent of sigma. Okay. So please make conclusion and give the numbers that you need to consider when you make conclusion.
Okay, so it is unaccepted since the percent sigma is 14.62, which is greater than 10%.
Okay, so you have to determine first which is the criteria, right? Which number is your criteria? So now you use 10%, so you will not accept it. Okay, that's correct. And okay, อาจารย์ถามพวัตหน่อยพวัต if you use the criteria of 30%, what will be your conclusion?
It will be accept ครับ
Yeah, it will be acceptable because 14, right? Yes, good. P to TV 14 now is less than your criteria of 30%. Okay, good. Okay, and the last thing that you need to do is some people take a look at this number. It's called NDC. Okay, number of distinct category. So it tells you the like the grouping, the numbers of group that of the measurements that can be distinguished by this measurement system. It's pretty hard to understand, but this number, okay, should be graded. Okay, usually we need greater than 4 if I remember it right. Okay, greater than that means our measurements variation is pretty small compared to the total variation. Okay, but mainly, okay, the indicators that we should take a look as P to TV, which is at this position. Remember that. Okay, come back. So you can answer question number 3. Okay, accept the precision or not. Okay, please tell the numbers that you consider. Okay, P to TV and also the criteria. Okay, and the last question, what do you think should be improved first, repeatability or reproducibility? Okay, so come back. Okay, almost last question. Oh, sorry. This. Okay, so which should we improve repeat or reproduce ขอสุภวิทย์หน่อยค่ะสุภวิทย์ค่ะ
ครับ
So 14, okay, is greater than 10, right? So unacceptable, right? So if we do not accept the precision, we have to improve it by reducing the variation, right, of the measurement system. And now the question is, should we reduce the variation regarding repeatability or reduce the variation regarding reproducibility? So which numbers you should take a look at?
เพื่อจะให้เป็น acceptable ใช่ไหมอาจารย์
ตอนนี้มัน unacceptable ถ้าเรา use criteria of 10%, right? Because 14, okay, is larger than 10%, right?
ครับ
Okay. And now question is, we have to reduce the variation of the measurement system, right? And the question is, should we improve repeat or reproducibility performance? Which numbers are you looking at?
14 ก็ต้อง reduce ป่ะครับอาจารย์
ใช่ต้องลดเนี่ยแต่ต้องลดส่วนไหนนึกออกปะเพราะว่า variation ของ total gauge INR เนี่ยไอตัว variance total ทั้งหมดเนี่ยค่ะของระบบการวัดทั้งหมดเนี่ย gauge INR เนาะมันประกอบไปด้วย variance ในส่วน repeat ใช่ไหมบวกกับ variance ในส่วน reproduce นะคะโอเคคราวนี้จะดูว่าเราควรจะ improve ส่วนนี้หรือส่วนนี้เราควรจะต้องไปดูตัวเลขไหนในตารางเนี่ยค่ะ
ก็เป็นตัว repeat ครับอาจารย์
เพราะดูเลขยังไงเอ่ย
ครับนะ
คำตอบก็คือ compare ใช่ไหมเดี๋ยวนะอาจารย์ไม่เพิ่นจะหมดเวลาหมดเวลาไปแล้วขอโทษทีอาจารย์เลยจะพูดงั้นอาจารย์เฉลยแล้วกันเนาะเดี๋ยวจะเลยไม่เลยเวลาไปเยอะก็คือว่าเวลาจะดูว่าเราจะ improve ตัวไหนหรือ reduce variation ตัวไหนแล้วก็ดูว่าตัวไหนมันมากกว่าไงอย่างในที่นี้ซิกมาเชื่อซิกมาคือตัวบอกความผันแปรใช่ไหมความผันแปรของส่วน repeat มัน 0.028 ใช่ป่ะในขณะที่ของส่วน reproduce มัน 0.006 ใช่ไหมงั้นซิกมาในสูตร repeat มันเยอะกว่าซิกมา reproduce เยอะใช่ป่ะคะเพราะฉะนั้นเราก็คือควรจะเน้นลด variation ในส่วน repeatability เนาะโอเคไหมในส่วน reproduce มันน้อยนะซึ่งมันก็ confirm ด้วยการที่อโนว่า reproduce มันคือความแตกต่างของคนถูกไหมความแตกต่างของคนนะเพราะฉะนั้นคนเนี่ยมัน p value เนี่ยมันมากกว่า 0.05 คือมันไม่ต่างใช่ป่ะเพราะฉะนั้นคน4คนเนี่ยให้ค่าวัดโดยเฉลี่ยที่ไม่ได้ต่างกันมากนะไม่ต่างกันอย่างมีนัยสำคัญเนาะมันก็เลยทำให้ไอ้ค่า variance นะที่เรา observe ออกมาเนี่ยจะดูเป็น variance ก็ได้เนาะหรือจะดูเป็นโทษที variance ก็ตรงนี้หรือจะดูเป็นค่า sigma ก็ได้นะซึ่ง sigma ตรงนี้มันก็เลยจะมีค่าน้อยนะคะ
ครับอาจารย์
โอเคจ้ะงั้นก็เกือบหมดละ last question แล้วนะก็คือOkay. Question number 5. The two types of verniers measure the same parts. Okay. Why do they give different precision levels? ถึงคำถามงงมันทำไมมัน give different precision level precision เมื่อกี้เราดูจากนี้ใช่ไหมเนาะP2TV เมื่อกี้จำได้นะของ Digital Vernier เนี่ยนะมันเป็น 14% นะจำได้อยู่นะแต่ถ้าเกิดเรามาดูของ Manual Vernier นะมันจะเป็นเลขนี้ค่ะ 86% 86% ทำไมมันต่างกันเยอะจังทั้งที่มันวัดพาร์ทเดียวกันเลยนะพวกเราลองคิดนี่คำเรื่องสุดท้ายแล้วที่นายอยากจะพูดเรามีอาจารย์ compare นะเรามี manual vernier ใช่ป่ะกับ digital vernier เนาะ manual vernier เนี่ย resolution เนี่ยคือมันความละเอียดของมันวัดได้ในระดับ0.05 มิล คือจะละเอียดลงไปกว่านี้ไม่ได้ละในขณะที่ดิจิตอลเวอร์เนียละเอียดระดับละเอียดกว่า0.01มิลโอเคไหมมันห่างกันได้ทุก0.01มิลนะในแต่ละค่าวัดอะค่ะโอเคแล้ว manual vernier เนี่ยเดี๋ยวนะโทษทีเขียนไว้ตรงไหนแล้วเนี่ย manual vernier เดี๋ยวใหม่นะขอไปเขียนใหม่หายแล้ว manual เนี่ย resolution นะ 0.05 ในขณะที่ดิจิตอลนะ 0.01 แล้วก็ค่า P to TV ratio ใช่ป่ะเมื่อกี้อันนี้ 14% อันนี้ประมาณ 86%โอเคคำถามคือ2ตัวนี้มันก็วัดด้วยสี operator เดิมเหมือนกันพาร์ท10พาร์ทเหมือนเดิมเหมือนกันแต่ทำไม P to TV นะมันต่างกันเยอะจังคิดว่าเพราะอะไรเอ่ย
resolution มันต่างกันครับ
ใช่ถูกต้อง resolution มันต่างทำไม resolution หยาบอันนี้ resolution หยาบใช่ไหมมันถึงให้ค่า P to TV ไม่ดีเลย
มันค่าความห่างมันเยอะครับ มันทำให้แบบทำให้ค่าที่วัดไปได้มันอาจจะแบบโดนปัดขึ้นหรือปัดลงทำให้มันยิ่งหยาบครับ หรือเปล่าครับ
ได้ค่ะ
ขอลองต่ออันนี้อีกที
ค่ะเดี๋ยวรออาจารย์แป๊บหนึ่งนะคะ พอดีอาจารย์เน็ตหลุด
ฮัลโหลขอโทษทีได้ยินเสียงอาจารย์กลับมายังคะ
ได้ยินแล้วค่ะ
ขอโทษทีนะพวกเราเน็ตหลุดไปเพิ่งจะเข้ามาได้เดี๋ยวอาจารย์สุดท้ายแล้วก็คือเรื่องเมื่อกี้พูดไปถึงเรื่อง resolution อยู่เนาะใช่ไหมตรงเนี้ยค่ะนะเหตุตอนนี้เนาะเหตุผลของการที่ operator 2 คนให้ precision ไม่ใช่เอาใหม่ manual vernier เนี่ย precision แย่ใช่ป่ะกว่า digital vernier เยอะเนาะเมื่อกี้เพื่อนเราคนนึงช่วยตอบแล้วว่าเป็นเพราะ resolution มันหยาบกว่าใช่ป่ะโอเคนะอาจารย์เลยจะชี้ให้เห็น data ตรงนี้ค่ะว่าพอ resolution เป็นจุด5สมมุติว่าครั้งแรกได้จุด 24.05 ครั้งที่2ถ้ามันจะเป็นมันก็เป็น 24.10 เลยใช่ไหมคือมันต้องกระโดดขึ้นไปทีละ0.05ในขณะที่ดิจิตอลเวอร์เนียมันละเอียดกว่าคนนี้เวลามันต่างกันทีมันต่าง0.01นะคะเพราะฉะนั้นเวลาคำนวณค่า r เนี่ยไอเนี่ยก็ต้องต่างกันประมาณในสเกล0.05อันนี้ก็อาจจะต่างกันในสเกล0.01ได้ในเวลาคำนวณค่า r bar นะคะ r bar อันนี้มันก็จะน้อยกว่าใช่ป่ะกรณีของข้างบนเนาะเพราะฉะนั้น r bar เป็นตัวกำหนด sigma repeat ใช่ไหม sigma repeat ของ digital vernier ก็มีโอกาสจะน้อยกว่าเพราะฉะนั้นมันก็เลยทำให้ sigma ของระบบการวัดมันน้อยกว่ามันก็เลยทำให้ precision มันดีกว่านะคะลองไปคิดตามดูแล้วกันเนาะแล้วก็เรียบเรียงตอบมาในคำถามนี้นะ question ที่5อันนี้นะคะนะโอเคเห็นตรงนี้อาจารย์ทำให้ดู example หนึ่งนะของด้าน digital vernier ใช่ไหมพวกเราฝากไป fill in ข้อมูลนะคะตัวเลขที่เกี่ยวข้องแล้วก็เราไปทำเองสำหรับกรณี manual vernier นะโอเคนะคะแล้วก็ส่งอันฮีทชีตนี้นะคะก็ภายในเราสอบกันวันจันทร์หน้าแล้วใช่ไหมคะนะอันนี้ก็ส่งวันอาทิตย์ใช่ไหมมายปกติ
ใช่ค่ะใช่ค่ะ
ส่งวันภายในวันอาทิตย์หน้านะสอบวันจันทร์หน้าก็คือเดี๋ยวอาจารย์จะโพสต์ไปในคอร์สวีอีกทีนึงนะคะเรื่อง instruction การสอบนะอย่างเช่นก็คือให้ open book ได้แหละอยู่แล้วนะเราสอบออนไลน์นะคะพวกเราวันเวลาสอบเนี่ยก็คือเช้าวันจันทร์หน้าถูกไหมมีใครดูตารางสอบแล้วปะคะอาจารย์เข้าใจว่าคือ8:30วันจันทร์หน้าใช่ไหมคะ
อาจารย์ครับขอเป็น9 โมงได้ไหมครับ
อ๋อพวกเราได้จ้ะไม่มีปัญหาพวกเราได้กันหมดทุกคนก็โอเคไม่มีอะไรต้องต่อเลิกเที่ยงได้ใช่ไหมโอเคไหมคะเดี๋ยวนะตอนนี้ทุกคนอยู่ในห้องปะขอเช็คก่อนห้องเรามี12 คนใช่ไหมมาย
ใช่ค่ะอาจา
แต่ตอ
ร
น
ย์
นี้มีอยู่9 คนไม่รู้สิเพื่อนอีก3 คนเขาจะติดอะไรหรือเปล่าล่ะจะมีสิทธิ์ติดอะไรไหมพวกเราว่าไงถ้าไม่มีใครติดอาจารย์เลื่อนให้ได้อ่ะค่ะงั้นเดี๋ยวเขียนไปในไลน์กรุ๊ปก็แล้วกันไลน์กรุ๊ปมี12 คนใช่ไหมเนาะมายจ๋าโอเคคนอื่นๆก็คืออยากเป็น9 โมงใช่ไหมคะมีใครติดขัดกับ9 โมงไหมที่อยู่ในมีตติ้งตอนนี้จ้ะ
ไม่ติดครับ
โอเคค่ะงั้นถ้าไม่ติดเราเซตอัพเป็น9 โมงก่อนแต่อาจารย์ขอถามคนที่ไม่มา3 คนนั้นก่อนนะเพื่อ make sure ว่าเขาไม่ติดอะไรนะคะ ถ้าไม่ติดอะไรก็เดี๋ยวก็เป็น9 โมงวันจันทร์หน้าแต่ถ้าติดก็8 โมงครึ่งวันจันทร์หน้านะคะแล้วก็ข้อสอบก็เป็น open book นะโอเคเพราะฉะนั้นอาจารย์จะไม่ได้ให้ตารางตัวเลขอะไรอย่างเงี้ยเนาะเราก็สามารถเปิดได้ในเอกสารที่เรามีนะคะแล้วก็มาเจอกันใน Microsoft Teams นะคะก่อนนะแล้วเดี๋ยวอาจารย์เขียนไปในไลน์อีกทีนึงแล้วก็ในคอร์สวิวสมมติเราสอบ9 โมงนะคะเดี๋ยวเรามาเจอกันสักตอนแบบ8 โมง 50อะไรเงี้ยนะคะก่อนเพื่อที่จะซักซ้อมทำความเข้าใจนะคะแล้วอาจารย์ก็จะพาเราเข้าไปในเว็บไซต์ที่จะทำข้อสอบนะแล้วก็เดี๋ยว instruction ก็จะบอกตามนั้นนะคะงั้นเราก็เตรียมตัวก็คือเอามีเอกสารที่เราต้องใช้สูตรเสิร์ชเลยนะแล้วก็มีเครื่องคิดเลขนะคะแล้วก็เดี๋ยวนะมีอะไรอีกกระดาษทดอะไรอย่างเงี้ยนะถ้าเราอาจจะต้องใช้บ้างนะคะก็เตรียมมาให้พร้อมนะตอน8 โมง 50แล้วเราเจอกันนะคะโอเคมีคำถามอะไรเพิ่มเติมไหมคะ
ข้อสอบยากไหมครับอาจารย์
ข้อสอบไม่ยากหรอกคือถ้าเราทำตามในเวิร์กช็อปได้ค่ะเราไปดูนะในเวิร์กช็อป4 ครั้งคือไอ้ครั้ง AAA นี่ไม่ออกสอบใช่ป่ะตั้งแต่เรื่องของ control chart process cap ใช่ป่ะ MSA ก็จะมีเรื่อง linearity กับ bias คราวที่แล้วแล้วก็มีเรื่อง gauge INR วันนี้เนาะถ้าเราทำได้อะตามคำถามที่อยู่ในเวิร์กช็อปเนี่ยก็ทำข้อสอบได้ส่วนใหญ่แล้วล่ะนะคะแล้วก็อาจารย์ก็จะมีโพสต์ที่เป็นเว็บไซต์หนึ่งใช่ไหมที่พี่มายใส่ไปในไลน์นะก็จะเป็นตัวอย่างโจทย์เกี่ยวกับเรื่องเหล่านี้ค่ะพวกเราไปฝึกทำแบบฝึกหัดตรงนั้นดูนะก็จะทำให้เรามีประสบการณ์มากขึ้นนะในการวิเคราะห์นะแล้วก็ทำข้อสอบนะคะโอเคไหมพวกเรามีคำถามอะไรเกี่ยวกับเนื้อหาหรือข้อสอบไหมคะที่อยากถามอาจารย์ตอนนี้โอเคถ้าไม่มีเนาะเดี๋ยวก็คือ instruction ของข้อสอบก็เป็นตามนี้นะคะแล้วเดี๋ยวอาจารย์เขียนบอกอีกทีหนึ่งก็แล้วกันเนาะใน course view กับในไลน์นะคะโอเคพี่มายช่วยไลน์ถามน้องหน่อยแล้วกันนะคะเรื่องเวลาสอบนะจ๊ะว่าเป็น9 โมงใครติดอะไรไหมแต่ถ้าสอบ9 โมงให้มาเจอ8 โมง 50ถ้าสอบ8 ครึ่งก็มาเจอกัน8 โมง 20นะโอ
ได้
เค
ค่ะ
จ้า แล้วก็ทุกคนอีกอันนึงนะก็คือว่าสอบก็เดี๋ยวให้เอาตั้งกล้องอะค่ะถ่ายตัวเองไว้ด้วยเนาะเพราะอาจารย์ก็จะเหมือนกับสอบจริงอะเราก็จะเห็นหน้ากันอะไรอย่างนี้ใช่ไหมนะแล้วก็ทุกคนก็นะเราโตแล้วปี 4เราจะจบไปทำงานแล้วนะเพราะฉะนั้นเนี่ยข้อสอบเรื่องวิชานี้ไม่ยากหรอกขอพวกเราเนี่ยถ้าอยากได้คะแนนดีขอให้พวกเราอีกอาทิตย์หนึ่งเตรียมตัวดีๆให้เพื่อนช่วยติวได้ในช่วงก่อนสอบแต่วันสอบนะอาจารย์ขอให้พวกเราเนี่ยซื่อสัตย์กับตัวเองคือทำเองข้อสอบเรารู้อยู่แล้วใช่ไหมเราต้องไม่ทุจริตเราทำเองนะคะเพราะฉะนั้นนะอาจารย์อยากให้พวกเราเนี่ยต้องภูมิใจในตัวเองที่เราเป็นคนที่ทำเองแล้วเราจะไม่ให้ขอความช่วยเหลือจากใครแล้วก็ไม่ให้ความช่วยเหลือใครนะตรงนี้มันเป็นเรื่องที่เราต้องมีติดตัวไปเองนะคะอาจารย์ก็ฝากพวกเราจะคิดตรงนี้นะโอเคนะแล้วก็ระหว่างนี้ในสัปดาห์นี้ถ้าไม่เข้าใจตรงไหนนะติวกันกับเพื่อนเนี่ยอาจารย์ว่ามันก็จะช่วยเยอะเนอะแลกเปลี่ยนกันเวลาเราสอนเพื่อนถ้าเราเข้าใจเราสอนเพื่อนได้เราก็จะเข้าใจลึกซึ้งเราก็จะทำข้อสอบได้นะตรงไหนที่ไม่เข้าใจจริงๆอยากปรึกษาอาจารย์ก็ถามมาในไลน์กลุ่มได้เลยนะคะนะ
เรียบร้อยแล้วค่ะ ไม่มีอะไรแล้วค่ะทุกคนออกจากมีตติ้งเลยก็ได้ค่ะ เจอกันวันสอบนะคะ
ขอบคุณครับ